This is now on. It's on, so we maybe wait 1-2 minutes for the later person.
Oh, so we can start now. Okay.
Yes, so I think we can start. And the first talk of today is by Jason Hall about signature of spin and charge, signature from thermodynamics and density measurements. Thanks.
Thank you for coming to such an early talk, and this talk is really aimed for the experimentalists who work on atom microscope experiments, and I'm grateful that a number of them and their groups are in the audience. While I'm also grateful that I think today there are many numerical people doing the computations are here, and I also want to present to them a hopefully they will find it a neat problem. The topic is really about the Fermion hybrid models, and I think there are a number of. I think the goal for us is to help the condensed methods to resolve long-standing problems and then to resolve a lot of conceptual difficulties which they have been struggling for so many years. So therefore, I was hoping that we can do experiments to answer to determine results and to answer questions with certainties. So some of the questions I would like to answer, at least address in the talk, is that what are the observable effects related to holons and spin-ons, if there's such a thing, and then what controls the motion of the holes. I think we have heard two talks, one experimental talk, one theory talk yesterday from the Harvard group, and the third question is that, which I'll come to at the very end, is suppose we are able to get to a temperature 10 times lower, say maybe 50 times lower in the two-dimensional hybrid model. Is it possible to see the effect of pairing? And if not, if in the unfortunate case not, are there any ways that we can really determine the pairing, in particular to answer the question whether this model has anything to do with with D-wave superconductivity and high-T superconductors. The talk is based on these work, and basically one of them is on hybrid model, the other one is on the TJ model, and I will convince you that at the sufficient low temperatures, then the two models are the same, and a lot of in fact, I think a lot of the ideas actually was established long ago by Professor Wang Zhengyi at the Institute of Advanced Studies in Beijing, and he has been working in this direction for many years. However, I think the communication between the co-atom community and the certain fraction of the condensed community is not very efficient, and there's a lot of language barriers. So, but what I will talk about a lot today about the so-called the concept of phase strings, and then is something that is established by him some time ago, and so here is some. I would like to make the point that there is a considerable merit rather than thinking about a two-dimensional square lattice. And let's first think about a ladder. A ladder is something of this form, that you have two legs and then the hopping, and then you can make the hopping here different from the hopping there. Horizontal and vertical are different, and then the TJ model, the hybrid model on the ladder would be this usual form, except that the hopping you can tune, and then the on-site interactions between different spins. And then one can also write the corresponding TJ model. This is understood to be no double occupancy, although it is deceptive to just write like this, but this means that I'm working on the subspace of the no more than one fermions. And then the question that I like to address is that if you have a half-field band and then insert one hole into the system, what would happen to it? And this is the entire talk. The entire talk, or the 99% of talk, is about this. And then the message I'm going to convey is also very simple. I'm going to tell you what the exact results are, and the exact results are based on exact diagonalization, and also the DMRG result, density matrix renormalization group results. And so they are in principle exact. So then the question is that once we have the answer, which you see, some of them are very unusual, then the question how to understand the collection. I mean, we will see many of them. It's not only one data. So there's a collection of data. Is there any simple way, any consistent way to understand them? And that will be the end of the talk. And then at the end, I'll come back to address the issue of if we are able to go down in temperature 10 times or 20 times, 50 times in the next 10 years, well, can I see pairing in 2D hybrid model? Right. So now, but of course, in doing experiments, then one have to. I mean, let me first address some experimental issue first to do this. But then one really have to create a model with every size field except one of them. But in general, when you prepare a sample, when you do, take pictures, one may not be getting this. I mean, one may be getting maybe sometimes doublons, but now doublons you can, in principle, still get to low temperature. Maybe you can eliminate them, or maybe sometimes you get 2 holes, 3 holes, etc. So I think one typically would have to, you do a lot of experiments, and then you have to select from the experiments that, because every time you take a picture, then you have 1 hole, and then or maybe 3 holes, etc. And then you have to collect, select out from the data that you have 1 hole, and then you average out all the 1 hole pictures. And then by post-selecting the data and also averaging over the post-select data, I think one can then compare with the result that we are going to talk about. Let's see, where's Christy Chu? And then yesterday she mentioned that, well, I mean, at the end it was basically telling the audience, look, don't complain because I do, you say 20,000, something like that. I am sorry, 60 to 80,000. But yes, but there's a gain. I mean, if one has to do 10 times the work, but you get 100% of that certainty, I think one may be worth it. So so here, let me just tell you about what we find out and just keep showing you the data. So so these are the things that one would find. So you have a two-leg ladder, and put a hole, and then you look at the ground state, and then once see. If you have only one leg, then you put a hole in, and then the hole moving around with spin charge separation. Then things are very uniform, and then you don't see any density oscillation, etc. However, you have two legs, then you see a pronounced density oscillation, as I'm going to show you soon. But if you have three legs, you don't see anything, and then you have one hole, you see something. You dump another hole, you also don't see anything, and if you weaken the bond, you also don't see anything. We gradually weaken it. And if you produce imbalance, don't see anything. But then if you don't do any of this, just simple thing, and just put a hole in, then you see oscillation. And the oscillation, and then so I'm going to show you the data. And not only oscillation, and there's a pronounced feature also in the momentum distribution. They come hand in hand. When the oscillation disappears, those features in momentum distribution also disappear. And now, and so why do we care about this? I mean, you can always do some calculation on some system. Are there just details, or would it be able to address questions of principles? And then I hope to convince you, it is the latter. That I think the results exact results will shed considerable light on the basic mechanism of the motion of a hole. And the large oscillation, large collection of phenomena has a simple explanation in the so-called phase string picture, which I shall explain, which is the phase fluctuation caused by the spin backflow. And these results are exact, and they can be used to calibrate proposed theories. The physics, although very subtle, is actually very transparent. And the many features can be obtained even by back-of-envelope calculations. And then that is the message that I like to convey. Now let me show you the data. So this is just I think the experts in the audience know how to do all these calculations. I mean, either you do exact diagonalization of the hybrid model, and or you do the MRG, and then this is is two-leg ladder. You can do very long chains, and then I think my colleagues have done up to 400 something. And so here is a short train. I asked them to do a short train because at that time I thought that, wow, maybe this is easy to do experiment, because I think it was I was told that for long chain 200 sites, and you see all these oscillations. And I asked them, would you be able to see in a shorter chain? Now, how small a chain can you see? So this is the very small chains, only 12 sites, and then 20 sites, 40, and then you can go up to 200. You can still see all these oscillations. The U over T, these are the parameters of hybrid model, which I'm not going to. I think I don't need to explain to the audience. So for sufficiently large U over T, you see these oscillations. And now let's see what happened. I think so early on, and then Professor Wang Zhengyu and his group, and actually for many years, they have done a lot of calculation for TJ model. Now the reason I would come back to the TJ model is that because there is a considerable body of work in the literature by his group and by other people on TJ model, and the discussion I'm going to talk about, say the so-called phase strings, is also based on TJ model. Although it can be generalized, it has a generalization to in hybrid model, but the TJ conceptually it's simpler. We don't have to do that, but this picture is just to show that the two models are the same, but essentially the same. They have the same qualitative feature. Here's the hybrid model. I mean, some black curve, and then the blue ones are the TJ, and then one of them are one of them is charge density or particle density. The other one is spin density, and but this the people in those studies often plot this is actually the whole density, the density of holes, and experimentally we measure particles, and then you just need to invert them. So when you measure particles, and then these are the say the spin up would be the black curve, and then spin down would be the open curve, and then when you have spin up, spin down, and then you can form the total density, and then so basically you see everything is oscillating. And then the
Are the T's and U's and J's consistent? Because the ratio seems to be very off. I mean, I know the figures agree, but the numbers don't seem to be. No, on the left side. Right. Yeah, it's consistent. Okay, good. That's fine. He knows the numbers exactly. I just know the ratios.
who happy to answer the question? Thank you.
It's good.
Thank you very much. Thank you very much. Yes.
This is a two-leg ladder. Is it both legs are looking the same?
Oh yeah. By looking the same meaning.
So what are you plotting here? You're plotting one leg or the
Oh no. Yeah, sorry. That's okay. Yeah.
Either
No.
leg looks the
Yeah.
same,
So
doesn't
excuse me.
matter.
Yeah. So the density by density, one means that one's adding the density of both legs, and then spin of both legs. So basically, you think that is it. So excuse me. Yeah. Right. Thank you for very much for clarifying, but otherwise it will be confusing. So basically, when I plot the density and spin density, I have two legs. It's just looking up, counting all the spins.
Just a quick question. The negative density, what's the...
No, it's not density. This is spin n up minus n down. Those therefore, okay, that's the. So now, excuse me. So what happens if we dump two holes in? Now here's a typical situation. For example, if I have one hole, then then this is spin density, and then also the total density. But then once I put in two holes, everything's very smooth. Then again, this continues for arbitrary lengths that you can find. And then now what happened is that if you weaken the bonds like so, suppose I change alpha to be very small, and then when, of course, in alpha is really small, then this becomes individually separated. But when you turn it down from 1 to 0.4, then all this oscillation before becomes again disappear. So again, it shows that the oscillation. It just shows you the direction of where the oscillation disappears. The third one is that now I'm going to spin imbalance it. Suppose I have more up particle and down particle. I don't know where they distribute. And then so suppose you start out with more up and down, and then again you want so you put in one hole, but the background has more up spin than down spin. This also weakens the oscillations. So there's also many directions that one can weaken the oscillations, and then the question is why. The last thing I'm going to show is that if I look at the momentum distribution, then one discover, again, this is for different alphas, and then sometimes it have a peak, but then when there's a peak, and also the charge oscillation disappears. But then when the charge oscillation occurs, the momentum distribution has split into two peaks on both sides. So the existence of the splitting of the peaks come hand in hand with the oscillations. And that's just meaning that this guy is actually mobile, and he has a momentum. Questions?
What are the boundary conditions?
The boundary, also, it is open boundary, so it's a finite chain, and then there's just no more coupling, right? So you can think about a chain that have a T and go to 0. So, right. You can think of hard wall, yeah.
Do you require a flat potential, or do you require a flat potential, or does all of this also hold in a track?
The calculation were done in flat potentials. We can discuss the reason. I don't think it will change very much with and for the physics reason we don't talk about. Yeah. But it can be done. You can we haven't done the harmonic potential. So, so I would like to. So these are numerical results. I mean, we are, and the question is that is there any physical way or even analytic way to understand this phenomenology? And I would like to present an explanation. I would not call it a proof, but I would think it's very convincing. And then the first two are vigorous results. And then the first result is on the so-called Marshall sign, is about the nature, the ground state of an antiferromagnet. The second thing is a formal result about the propagator of a hole in a antiferromagnetic background. The result is this result is the starting of the idea and the picture phase string. The result is, as I say, you see, is a formal result, and it tells you about where the spin black hole comes from. It is not computationally convenient in the sense that if you still use it, you might have to run the program. But on the other hand, but just making a simple approximations or a simple simplification for this propagator formula, one can immediately gain and then that formulation amounts to the so-called saddle point approximation, and then picking out the dominant contribution. And then once you present the whole collection with a dominant path, and then the dominant path have a phase associated with it, then one can actually explain everything that I mentioned to you about. So I first tell you about the two exact results, and then I'm going to tell you how the exact result explains how this result after the simplified picture can be explained, can explain the previous pictures. Results. So the first thing is about the so-called Marshall sign, and it is written it's presented in the paper by Marshall in 1955. During that time, there's a beginning interest of quantum spin models, and in the paper he credited the argument to Rudolf Peierls, and the argument is follows. So I can, by the way, where is Christy? Yeah, right. These symbols are Harvard symbols. These symbols are Harvard symbols. I saw it in the picture yesterday. I find it actually much easier to see than the up and down arrow. So to the Harvard credit. So no matter how the Marshall, so the point actually the important contribution is that even though I don't know what the ground state is, I can still tell you some relation about the ground state, and he's saying that now I can always expand any state in terms of the spin. When you can write down spin bases, and then there are two of n terms, the zillions of them, and by the way, I also want to mention that these up down pictures are very deceptive in talking about antiferromagnets, and can get people into great trouble because the system is not like this. The system is, and then therefore, Richard knows very well. There are some work by Anderson that show that antiferromagnet can be written as a distribution of mixed RVB bonds, and then for different distribution size, and you average them. If the range is long enough, then you get antiferromagnet. But in that formulation, every single wave function is completely screwed up. It's not up down like this. So all it says is that there are a lot of up down correlations. But the very fact that even in one dimension, the depletion or metallization is 70-something%. It means that this is a very bad picture. So there's a lot of mixture. Even though I flip a little bond, and then the tradition will say, wow, it's very bad. No, it's not very bad. There's a lot of them there. And so there are zillions of them. But Marshall is saying that there's some relational coefficient that if I flip any spin, any pair from here to there, I change the sign. So Marshall is saying that the coefficient, first of all, are real. Secondly, then when you flip them, you change sign. So it must be something like that. If you fix this sign, then the rest of them, you have no choice. In this case, if I flip this spin, then I go from plus to minus. And then here I flip this spin plus and minus. If I flip two of them, then would be plus again. That is the Marshall sign. Now, now what would happen if I create a hole over here? When I create a hole, I say I take the previous picture, I create a hole. But for this guy, it goes 0. Why? Because here this is a down spin. If I kill off with that, then I kill off this guy, and then so that's why I have contribution here. Now, what happened that now if I consider the other state that I have moved the hole, I create the hole, the next, say one step down, and now it kills the spin. But then for this, because First, I've exchanged this spin, and then this become non-zero, but all the other ones 0. Now, I don't mean this picture. Do not mean to say that when you add one hole and then there's only one coefficient that will match together. There are zillions of them. So actually, there are, somewhere down here, then the other term can match this term, which I haven't written down. In fact, there are 2 to the n terms, and then so basically create a hole. You can zoom. You can produce a lot of the holes in each component, and then everyone propagates, and then you collect them. Yeah, then through here, and each time you proceed, say hop to here, you change the sign. So basically, hopping from one side to the neighboring side will involve a sign change. And then the spin and the sign change represent the spin black flow. In other words, a spin black flow must involve a Marshall sign change. And in addition, one had to sum over all the spin configurations. There are many of them. So, questions, please. Oh, the original proof is yes and no, but it would take it would take a digression. No, it's actually a clever observation. That. Already?
Yes.
Are you serious? Oh, my goodness, I don't have to stay up so long. Okay, I didn't. Okay, well, I apologize for the I didn't know. So this is done by Professor Wang Zhenyi, and say, well, now I'm going to look at the propagator. Sorry about the speed of my English. So he's saying that, well, I'm going to look at the propagator, and then the propagator, now you can rewrite it like this, and this is the on-site thing, and then the propagate. And then so when you look at this, you discover that I have this collection of wave function come in here, and then this is a J, which is a local, and then zoom, it makes up a lot of spins, and then every time, and then you mix up a new configuration, and you propagate one time, and then again you mix up, and then you propagate. So this is the process of propagation, and he found the final result that he can show that this is the Green's function can be written in this form. That there is a it cannot be 5 minutes, but anyway. So something is the positive, and then there's a collection of change the Marshall signs, which is these are really just all plus 1 minus 1, and depending on the path. So here's the general because I screw up with my time. So if I propagate from, there are many different paths from 1 to, so conceptually something like that, many paths from I to J, and for each path there's lots of spin oscillations, and then like this, and then they can but each one of them are associated with a set of spin flip, because whenever for any spin configuration, when the hole moves around and you see it encounters a exchange with let's say with upspin, and then or with a downspin, and then each time then there is a change of sign, and then that is so this collection thing actually the number of downspin. You can make it upspin also, but then let's say a downspin. well, with a -1. So that is the concept. Now the question is that this although formally exact is very inconvenient to use, and although it has a nice picture of the spin stirring, and then so now we are going to make a simple approximation saying that among all these terms there's one dominant term. Well, there's a one dominant for any given path. There's one dominant spin configuration, and then it will give me a average. The phase, and then average of the phase. So I replace all this by this small amplitude. Now, once you do this, then the whole thing looks like a wave function. And then the wave function would now looks the following. That now you can it's very fast now, and because so at long distance, and then for example the
Just relax.
are you realizing making a mistake?
2 minutes.
I see.
Please don't blow my eyes with your pointer.
I'm sorry. Yeah,
It's not my fault.
I did this many times. Okay. Since we are all friends, and with Francesca's kindness, I'm going to I'm going to because that's one more thing I need to say. So, but even if I assume there was one dominant path along here, and then there's a phase, and then the phase is again is given by the Marshall sign, which is a number of downspins. But now I can write the number of downspins, this total number of downspins, in terms of something like this. Is the length of the path versus basically the average number that I encounter spin flip. So this turns out to be key quantities that along a path, how often it's almost like a scattering process in a path, and how often you exchange with one of the spin species, and this controls basically all the periods that we're going to talk about. So with this picture, then for example, then I can rewrite this in terms of this fundamental quantity plus say this is length times the density of a spin flip. But then because of this property, so it looks like a wave. Now, however, because this property that two of this is just a number, like that two of this number is even, always 1, that means that either I of S is the same to either minus I of S. So therefore, if you have this wave, you also have this wave. And then now P is equals to, say, in this case, you identify the momentum is equal to this. Here, the momentum you can identify to be 2 pi minus this quantity. So the whole thing is symmetric around pi. Let me now show you. Oh, sorry, here's a density oscillation also. We can go forward. And the density oscillation, similar calculation shows that the oscillation is equal to 2 kappa. Oh, sorry. Kappa is actually related to P. So sorry about that. So what happened is that if you look at the momentum distribution, this shift, that shows that there are 2 peaks. Once you have this P is not 1, and then one can also show that this shift is related to the density oscillation, and these are the data, so they come in hand.
So Jason, doesn't this argument say that in the 1D case you would get your oscillation in the single line?
No, because in the 1D case you don't have a phase string, so you don't have a phase. That phase string picture is due to the interference.
How about the 3-leg?
Three-leg, you don't get it. No, I'm going to explain all of them. Feature. That's why in odd number that you don't see that. Right? So now I'm going back to the beginning. I'm going back to just the oops, sorry. This very. This gave me. Just please. Yeah. I'm going to go back all these pictures. Why now in one leg? Then because but here the reason that it's not enough time. The reason that I get an oscillation because there are different paths I can interfere, and that's why I have this oscillation. In 1D I don't have this. I can go from here to there one path. Now why would I don't get 3 paths? Now one can understand it from the following basic ideas. Basically you pair up both of them. I mean, just experimentally, I mean, numerically, you don't see any oscillation. So basically, the rule is that we have 3, and you pair 2 of them, you end up with 1. And then now, so 4, you also see oscillation, but it's not as pronounced. Now, why do I don't see the 2 holes? What happens if 2 holes? You can also show the phase string of 2 of them cancel each other to a large extent. Basically, if you separate distance and they can move around, there's no effect of phase strings. Because the end cancel all the fluctuation around and cancel each other. So so this also shows that 2 holes, the phase string effects, and then there's some phase strings around there that actually ties the hole together. And then now you're weakening the bond. Now you weaken the bond, and basically the whole thing becomes opposed to the independent objects. And then in this case, you can actually show that the whole thing actually hops around and then as a whole. So therefore, like again, the motion is for this object is coherent. Now, raising the reason that you don't have the oscillation by raising the spin imbalance is that when you polarize a system, then of course you lessen singlet, so therefore it's also weakened. So everything can be interpreted as a consequence of the phase strength oscillations. So I'm 99% done. I had mentioned very early on that I would mention a comment on the prospect of whether, suppose I can get the temperature 10 times or 20 times, 30 times lower, can I see spin pairing? And that is related to the question of whether this model, I mean, how much of it is really responsible for high-Tc superconductors. The following is done by my colleague, Bill Pudiker, who is an expert in high temperature serial expansion. These are the result from high temperature serial expansion up to 12 orders. And that it's a longer series in TJ. And then he told me that the calculation in hybrid is much more difficult, but he's pursuing it. I just want to point out one thing that I think Francesca has practiced Kung Fu before. Now this is the spin correlation length. Even down to T over J for this is very low time, so they use TJ model. It's basically 0.1 T in nano. This is only about 1 or 2 lattice spacings. If you go down to the projection, is like go down to 10 times lower, then you don't have you may not be get much bigger. So if, ladies and gentlemen, the correlation length, if you after you work for pairing, not for the spin correlation, for pairing turns out to be a few lattice spacing, you don't see it would be hard to see any pairing correlation in the same magnitude as spin correlations. I think the one way to overcome it is actually have several layers. I mean, 2 or 3 layers. Then I think also maybe that some fraction of a high Tc people believe that the reason that you have superconductivity is actually a couple layers. Once you couple them, the correlation length can be expanded considerably. Thank you very much.
Thank you to you. I think we have time for questions.
Oh, really? We do?
Yeah, we do. You see?
The last slide behind you, is that for infinite two-dimensional lattice?
This one is for infinite two-dimensional lattice. This one is for this slide is for high temperature serial expansion, which is designed for infinite lattice.
So it's not for that anymore.
That's not too late anymore. Yeah, this one is completely separate questions.
Yes, please.
So going back to the idea that if I weaken the bonds, I stop seeing the oscillations. Is there a critical bond?
Yes, there is. Yeah. I mean, I think there is. By that time, but we have alpha 0.25, something like that. So, yeah, right, this way.
So what role does SU2 symmetry breaking play for the phase string story? Because the latter probably does not break it, right?
Right. So my understanding is that for example, I have labeled the phase strings as label the number of particles up, but then you can also label the number of particles down. I think, but so because I think. other aspects I do not know yet, but yeah, but that is yeah. But I think it can be. Well, okay, let me. It has been a very difficult process for me to understand this set of paper, and the reason I bring it to is not because it's related to my work, because I do think this picture has some merits worth considering, and as I say, the majority work is done by the group, and I think, and I became complaining to them, beating them up, saying that you have to speak in the language that is useful, and I think that we can, I mean, our community can help to make things as simple as possible, basically. Right? Yeah. Whether all the calculations are done 0 temperatures. What's your name, please? Yeah. The first part on the DMRG on the two-leg ladder are done 0 temperature. So therefore, temperature effect is very important. The last one I mentioned is done final temperature. You can actually see I cannot go down to 2. Yeah. So right. Yes. And then,
for the first part, if you do exact diagonalization, where you see the distribution of eigenenergies changes significantly after you add a whole. I just curious. Like the spectrum of eigenenergies.
you can get the spectrum. You can. I think. The problem for exact diagonalization is that one cannot do too long a chain, and then I think you know how long it can do. But it has advantage. It can do thermodynamics, and then my understanding maybe 8 to 10. So it's pushing there, and yeah, one can do some of the things that you mentioned, especially look at thermodynamics, but that is very important. And I don't expect the thermodynamics would change, well, at least for range temperature, change very much because the bulk is there's a gap there actually.
Okay, so thanks a lot again.
Thank you very much, Francesca.
I don't know.
I think I'm disconnected.
I was, yeah. It was fine a moment ago.
Yeah. Yeah.
Oh, there we are. Yay!
Okay, so let's move to the second talk, quantum dimer models with Corda. I will make a sign.
Okay, thank you very much, and I want to thank the organizers. This really has been, one of the best workshops I've been to. Some really, 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 really exciting experimental data and stuff have come out. So I'm going to talk about some stuff that was done with Bhuvnesh Sundar, which was a student of mine who's now at postdoc at Rice, and then Michael Lawler and Todd Rutkowski, who are at Binghamton University near Cornell. All right, so I always like to tell you the entire story on the first slide, so that you can tune out and don't have to listen afterwards, check your email, etc. So the setup is we're going to have atoms with large spins in optical lattices in limit of 1 atom per site. We're all very used to at this time that you get an effective spin model out of these. I'm going to talk about how to introduce an off-resonant photoassociation beam, which is going to convert this spin model into a dimer model, and then look at its phases, and we'll get some interesting dimer crystal phases and possibly some spin liquid stuff. So that's what's coming, and there's lots of details. Okay, so I'm going to begin just talking about dimer models. Why on earth would you care about dimer models? What's interesting here? I'll talk about how to engineer them, and then the details. Okay, so I'm going to go back to 1949, Linus Pauling, I think before he was into vitamin C. You're all very used to this motif from chemistry of you can describe quantum states of certain molecules by talking about where their bonds are. Okay, and you get, in fact, some quantum resonances between different bond patterns. In 1949, Pauling decided to apply this chemistry picture to solid-state physics and tried to come up with a model of metals and some, I think, correlated metals even, by thinking about these sort of resonating bonds. I don't think it was a very good idea, but it's what, but it was inspirational. And about 15 years later, P.W. Anderson was trying to understand the Heisenberg model on a triangular lattice. Right? And this is, of course, another story you guys know very well. I'll say it anyways because it's nice to just repeat these little tales to ourselves. So if you're looking at spin 1/2 Heisenberg model on a triangular lattice, you throw down one spin, spin up. Look at a neighboring site. Well, probably the best thing there is a spin down. Right? Well, now we're frustrated. We don't know what we're going to put here because if we put down, it's happy with this guy but unhappy with that guy. Okay? So what P.W. Anderson said is, well, let's use this idea of Pauling's and let's just take pairs of sites and we'll just form singlets. All right? And he wrote this down as a variational wave function, took a quantum superposition of all these singlets, and he got actually a really good energy. So this appeared to be a pretty good model for what's happening in the Heisenberg antiferromagnetic magnet on a triangular lattice. Great. 15 years later, high TC is discovered. You know, you have a hammer. Perhaps high TC has something to do with this RVB state, and a lot of people have ran with that idea. A year after Anderson came up with his idea of applying RVB to superconductivity, Roxar and Kivelson sort of did the mathematical formalizing of this sort of model and thinking about Hilbert spaces where you label the quantum states by a bunch of bonds connecting sites. And they think about, if I specify another set of bonds, it's orthogonal to this. And they came up with what is now the canonical dimer model that people play with. And I'll show you what that is in a short bit. And there's really some rich physics they found. There was interesting crystalline symmetry breaking phases as well as some liquid phases. And in the modern parlances, these liquid phases are interesting because they're topologically ordered. And there's some of the nice examples of topologically ordered states that we have. All right. And basically the rule in writing down states is I can write down any pattern I want, but I can't have any site involved in more than one bond. Right? This is an analogy to these spin singlets, which you can't make a spin 1/2 in a spin singlet with more than one other spin. Right? Okay. So this seems pretty esoteric. Why is it interesting? And it's actually a good example of a general principle that if you take quantum mechanics and add constraints, interesting things pop out. And it's particularly successful when you think about geometric constraints. So here, by a geometric constraint, I'm meaning that if I put a bond between these two sites, I'm not allowed to put a bond between those two sites. Okay. And I don't know if this is going to resonate with everyone, but one way I like to think about how adding constraints makes rich physics with quantum mechanics is actually thinking about some quantum computing things, about stabilizer codes, error correcting codes, which essentially you take some bunch of spin 1/2 and you add constraints, and lo and behold, you add enough constraints, you get your information delocalized and it's protected from any local thing you could do to it. Right? More generally, a lot of rich physics has emerged from trying to understand how to implement constraints in quantum problems. So a lot of, whenever people talk about emergent gauge theories, that's typically about trying to implement constraints.
So all these constraints on the dimers, this is just a snapshot, right? So as a function of time, they'll fluctuate and form bonds with another one.
Yeah, or if you're thinking about eigenstates, they're going to be quantum superpositions of these different things. Or if you're looking at dynamics, if you did start in one of these, you'd expect it to evolve. Absolutely. Thank you. Okay, so now this is the point in the talk where I should go and enumerate all the wonderful physical examples we have of these dimer models. And unfortunately, there aren't a lot of them. All right? And there's some actually good real physical reason for this. You know, so if we go back to Anderson and think about these bonds as being formed by singlets of spin 1/2 particles, okay, there's a problem is that, formally speaking, if I write down a state where I make singlets between these two sets of sites, and I write down another state where I make singlets between these two sets of sites, it turns out these aren't orthogonal. Right? They actually have a very large overlap, and I'll show you that in a second. And so that means that these kind of Roxor-Kivelson dimer models are not really realizable in a nice way by spin 1/2s. Well, that's easy, you say. Let's go to a higher spin. All right, so imagine you, oh, yeah, so here's the story. So here's the calculation. When I gave this talk to practice it to my group meeting, I made the students go and do this calculation. I'm not going to make you do it, but you can trust my arithmetic. So what I mean by this state here is that I form a singlet out of these two, and a singlet out of those two, and that's the quantum state I'm writing down. This one is this guy, and if you just multiply this out, you get 1/2. Right? So the overlap is quite large between these. Okay? And as I said, one solution is going to higher spin. So if I do the same thing with higher spin, so by this I'm meaning I'm making a singlet out of these, and if I write down all my Clebsch-Gordon coefficients and multiply it out, I get that this overlap is 1/2f plus 1, where little f is the spin, right? Or you can recognize 2f plus 1 as the number of magnetic sublattices, sublevels. Okay. And so you go to large enough f, you're going to have these are essentially orthogonal. Okay. The problem with going to large f is that if you look in electronic systems, which you know have some local spin, which is some moderately large f, the types of interactions you naturally get are not ones that favor singlets, rather than ones that favor a more classical nail order, typically, right? And you can kind of understand this, that one of the major sources of interactions between the spins is really exchanging a fermion, and that changes your local spin by like 1. Right? And so you just make small changes to your spin, and that tends to make them look very like classical spins. Right? So we're looking for a large spin system which is not just turned into classical guys sitting there. Okay? And so that motivates trying to think about cold atom systems and trying to engineer something there. Okay, so the starting point is something very familiar. I'm going to put 1 atom per site, and I imagine they have some large spin. And we're going to get our standard spin model from some super exchange. That one of these guys hop over there, they interact for a while, then hop back. Okay? And generically, if I'm working in at zero field, so that you have rotation symmetry, we can write this effective spin model completely generically by decomposing the total spin that you get when this one particle hopped over there. So I'm going to let capital F be the total spin of these two little f atoms. So say they were spin 2, capital F could be 0, 1, 2, 3, 4. And we can write this effective Hamiltonian as we sum over all of those values. And we have some coefficient, which is second-order perturbation theory, and a projector into making those pairs into that spin. Okay? And if you look at something like rubidium, these UFs are roughly all the same. If you look at lithium, they have a little more of a spread. And what we're going to want to do is we're going to try and find a situation where the f equals 0 term dominates. Right? So we want a negative term that wants to have nearest neighbors be in singlets. Okay. And as I said, for typical atoms, these UFs are all roughly equal. And so we need to somehow engineer things so that the U0 is much smaller than the other U's. Okay, so here's the crazy idea, and this is the I'll say more about it a bit later, but this is the place where I'll be attacked, which is, so one way to try and engineer different coupling constants in these different spin states is to use some sort of Stark shift, right? So imagine we have our two scattering atoms, which are inside one well of this optical lattice, and there's some molecular state. If we shine an off-resonant photoassociation level, that's going to shift these things, this level a little bit. And if the quantum numbers of these scattering atoms, if you can make it so that only for certain quantum numbers they're going to have this coupling, you're going to shift the state with those quantum numbers. Right? In particular, if this molecular state has a well-defined electronic spin, that's s equals 0, right, then we're only going to couple to it if these guys are an electronic singlet. Okay. And so if you look at the molecular physics, essentially what we need in order to get a well-defined electronic spin, we need a very weak spin-orbit coupling. Right? So we need a relatively light atom, something like lithium works well, or sodium even is not so bad, that there are some molecular states which have this property in either of those.
Eric,
yeah.
These atoms already close to being formed bound in the ground electronic potential, because if there are two independent atoms, you'll have a singlet triplet mixtures at large distance.
Yeah, so these guys are in a single well of an optical lattice. As I said, this is the part I'm going to get attacked on the. I think I'll talk more to you later. So maybe the short answer.
Eric, let me ask
Yeah.
something else. You said all the U's are equal. If we have fishbowl resonance, we can maybe tune one U, which means spin up and spin down, and we could even use the fishbowl resonance to tune it that maybe the U1 U up down is 0 or close to 0.
Yeah.
But this is not the singlet. It's just.
I know.
Selective hyperfine states in the magnetic field, and you don't want the magnetic field to break 0.
I know exactly. So here I'm wanting the rotational symmetry.
So it's really the fishbowl resonance where we would have one U almost arbitrarily adjusted by the magnetic field. It would be a U between two specific MF levels.
Exactly.
But this is not
Exactly. But I want this rotational symmetry. Right, and I want to exactly. That's what I said. And in some ways, this is one of those silly theory talks where I'm off in some land of something that's really hard. But it's and I'm fully aware of that. But I think it's useful to interject some thinking about what is the possibilities and why would this be interesting, and it's if you don't speculate and try to argue for why something's interesting, then you never bother doing it. So right, yeah. So with the caveat that there's a lot of stuff going on in the molecular physics. The likelihood of having a single line up here that you're coupled to is pretty low, etc. But if you're really naive and just do second-order perturbation theory, you're going to get a shift of your on-site interaction by some coefficient, which is going to sorry, I misspoke when I said this only couples to the f equals 0. This actually couples to all the f's, but it remains rotationally symmetric, so it doesn't mix the different f's. That's really what I want to say. If this was not an electronic s equals 0, you'd end up mixing the different f's, because the there's a directionality of the polarization of the light that comes in. Right? So that's really why I needed the S equals 0. Okay. Right, so you're getting a shift that's been proportional to your intensity of your laser and inversely proportional to your detuning. And you can do a little exercise in Clebsch-Gordon coefficients and calculate how these coefficients should be. And the key point is that they're a monotonic function of this big F. Right? So if initially all of these background U's are the same, you can tune this term in principle so that the U0 becomes very small, but all the others aren't made small. Right? And we just looked at some typical experiments looking at photoassociation and the strength of those lines and the lifetimes, and came up with this estimate of a few watts per centimeter squared should be enough to do this, though I fully admit there's lots of little things in there which probably need to be thought about harder. Okay. Anyway, so if you allow me to do this and get to where we only have this attractive interaction in the spin singlet channel, right? This model, this Hamiltonian, the space of singlet bonds, labeled by these singlet dimers, is going to be closed under this Hamiltonian. So I'll show you a little bit how that works. Okay. So I'll just use a set of 6 sites. This is, I think, enough that I can get my head around it. So if I take, so these are summing over all nearest neighbor terms. So if I look at, say, a nearest neighbor term where I look at site 1 and 2. All right, the state I wrote down here, well, site 1 and 2 form a singlet already, so this is an eigenstate. Great. Well, what happens if I instead act on 1, 4? All right. Well, after acting on 1, 4, I have to end up with a singlet on there. It's a projection operator. Okay. This operator is rotationally symmetric. This state is rotationally symmetric. So the thing I get in the end has to end up being a singlet. All right? I can't possibly be messing up anything that's happening on 3 and 6. All right? I'm just acting over here. And so the only thing that can happen is I have to form a singlet out of the other ends of these 2 bonds. Right? So the term in the Hamiltonian that's a projector on these 2 goes and flips this plaquette. Okay? We actually get something a little bit different if I think about, well, what happens if I worked on this bond here at 2, 3? Okay? Well, by the same argument, I'm going to end up with a singlet on 2, 3. And by the same argument, I'm going to act with a singlet between these guys. So even though the Hamiltonian only has nearest neighbor projectors, I end up with longer range singlet bonds. Right? But the space of all things, all different patterns I can write down like this, including long-range things, that's closed under this Hamiltonian. Okay? Yeah?
So these long-range singlets can in fact be arbitrarily long-range if I act on the right dimer configuration?
Exactly. And so but the Hilberts, if I specify, if I write down all possible, including long-range bond configurations, that space is closed under this Hamiltonian. You got a complaint?
There's a little problem.
Yes.
Spin have a little bit is unusual, but if I higher spins, there are 3 particles singlets and 4 particle singlets. So I can actually there's a sing because if you just add the angular momentum. So there.
Absolutely. So this does not exhaust the space of all singlets. Okay, but this is a space that's closed under this Hamiltonian. That I cannot, by acting with operators like this, I cannot generate any of those other ones. Because I just demonstrated, right? This is if I act on 2 sites that already form a singlet, I get back what I had before. If I act on 2 sites that don't form a singlet, well, they form a singlet, and then the other ends form a singlet. Right. I mean, it's also, you know, you can just sit down and do the Clebsch-Gordon coefficients as well. I mean, that's how we get the 1 over 2f plus 1.
And do you think the ground state is in this subspace?
Ah, good question. Well, so one thing you notice is that if I, actually this is a nice slide for this. Okay, so if I look at if I take some configuration here, and I look at all the terms here which act on sites, on bonds that I already have occupied, right? That's a diagonal term. And that makes this, if I have only nearest neighbor singlets, that gives you a large negative number here. Anything else I do is going to give me a less large negative thing, right? And so in particular, in the limit where little f is really, really big, that has to be the best. Right, so I can't guarantee without thinking harder that as f becomes small, you're not going to get some crossover, that something happens. Okay, so if I think about a large f limit, as I said, we're going to have a low energy space defined by making these diagonal terms large, which is just the nearest neighbor singlet space. Okay, then we're going to have terms which move us out of this low energy space. If f is large enough, we can neglect these or take them into account in second order perturbation theory. And then we have terms which move us around in this low energy space. Okay. And these sort of moves that we get are just flipping plaquettes. And for those who are familiar with Roxar-Kivelson, that's exactly Roxar-Kivelson's model, is that you take plaquettes and your Hamiltonian can flip them. And then if you do second order perturbation theory on these guys, you end up getting a term which penalizes having parallel bonds. You know, I'm not going to actually do things in perturbation theory, but it's just nice to know that this model maps onto Roxar-Kivelson. Okay, so what are the states you get from this model? So if I go to the large f limit, what I expect is that I'm going to get a dimer crystal phase, where you're going to get mostly nearest neighbor singlets, and they're going to line up in these sort of ladder type things. And the reason why these are favored is those plaquette flip terms. This is the kind of state that has the most allowed plaquette flips. Right, that all of these are flippable plaquettes. When, for instance, if I had a staggered, you know, if I had a bond here and a bond here, I wouldn't be able to flip this plaquette, and so I'd get less kinetic energy from those terms. All right, and this is known from the Roxar-Kivelson model. The triangular lattice is a little more complicated. It turns out that the ground state, as f goes to infinity, again from studying the Roxar-Kivelson methods, models, this is in the literature, is actually this what they think they call the root 12 by root 12 phase, where there's a unit cell that has 12 sites in it, and it is in a quantum superposition of two different shaped sets of plaquettes, where each of these plaquettes represents the resonating bonds. Yeah, this is far from obvious that this would be true. Right? But it's really exotic. I mean, seeing this would be cool.
So do you have a sense of how big the gap to excitations is for this?
It's pretty darn small.
So that's J over 12 or J over root 12, would that be a decent way to think about it?
Well, there's also this 1 over 2f plus 1 thing floating around. So I think it's even smaller in that. I think you also get that factor. Well, it's not 0. Oh, I guess an f goes to infinity, yeah, but you know, anyways. All right. So what we did is we're working with our finite f system. You know, we're not going to find an f equals infinity atom around, probably. If someone comes up with one, let me know. So we're gonna do a small system, do some, you know, write down. We have this Hilbert space, write down the Hamiltonian, some big matrix in the Hilbert space, and diagonalize it. Right. So we're going to be limited to pretty small systems. And to see what sort of phase we have, we're going to look at this dimer-dimer correlation function, where we look at the projector on two separate sets of bonds. Right. So I look at the projector of these guys into a singlet and the projector of these guys into a singlet. And more or less, you can think about that. What we're calculating is, what is the probability of finding simultaneously a singlet here and a singlet there. Okay. And to visualize it, what we're going to do is we're going to fix one set of bonds and change the others. And so I'm going to draw little pictures where between every pair of sites, I'm going to draw some colored thing, which represents what is the correlator between this pair of sites and that pair of sites. Is that cool? All right, so it'll be, okay, so we'll start with I don't know any F equals 100 atoms either, but we'll start with a large F because I understand what's supposed to happen in large F. All right, my reference set of sites are these two, I, J. I'm looking at the correlator of those two with all other pairs. So for instance, the probability of having a singlet on this bond and this bond simultaneously is 0, right? That the whole rules are I can't have a bond in that thing, right? And then there's a 15% chance of having both a bond there, and so on. You may ask, why is this 25%? Well, that's because there's 4 symmetry-related ladder states, and we're in a quantum superposition of those 4, essentially. Okay. Right. And so this is exactly what you would expect from a ladder. Okay, so now I'm going to show you the F equals 3. And depending on how you think about things, you either say, well, that looks like a ladder, or that certainly doesn't look like a ladder. So I would say with this size of system, we can't see if there is long range columnar order on this. We have a mean field theory, which I'll talk about in just a moment, which suggests there is a phase transition near F equals 2, which goes between, at small f, you actually get a Bose-Einstein condensate that's a polar state. And so certainly this may be indicative of either being near that phase transition or past it. There's also, we're kind of hopeful of trying to find some kind of spin liquid in this as well. And okay, so just to advertise the mean field theory, which was actually done by my collaborators a few years back. What it amounts to is writing exactly the Hamiltonian we have written down, and then do a mean field decoupling of it, and essentially do Bogoliubov and looks to where it could be self-consistent. Is what it is. And they did, in this paper here, they were looking at the case where they took the F equals 0 U to be different than all the other ones. And then this axis is looking at the ratio between those. 5 minutes? Great, perfect, that's just what I need. And so everything I've been talking about so far has just been where this ratio is really large, so it's over here. So as you see, that around F equals 2 or 3, they were predicting this transition. I would not expect this to be a very reliable theory, but it gives you some indication. Okay, next we have the triangular lattice, which had this more interesting spin pattern. And so if I look at the large F case, the F equals 100, indeed I get a pattern which looks very much like this cartoon that's in the literature. So I wrote that there were two equivalent sets of these plaquettes that should be in the ground state. I only wrote one of them because with this as our reference bond, only one of them appear. We have only one overlap with one of them, and you definitely see that there are these visible plaquette regions. Again, when I go to F equals 3, things are a bit more ambiguous. Okay. All right. So why were we looking at that particular measure? And the answer is because that's exactly the measure you can get in the experiment. So you can imagine using our same trick of photo association, but now going on to resonance. So this is very similar to some stuff that Randy's used to probe some spin correlations. And so then, if you tune this onto resonance, you're going to get an atom loss term, which is dependent on nearest neighbors being in singlets. And so what you would do is you'd set up your state, flash this on for a short time, take a picture, look at where atoms are missing, and bin that. Then you start over, flash on your resonant photo association, take a picture, bin that. And the histogram of where things are where pairs of atoms are missing is exactly the picture I was drawing on the last page. That's exactly what it gives. Okay. All right. So what are the problems with this? So Caden already asked about energy scales. You get pretty strong, pretty small gaps to excited states, and so there's really high sensitivity temperature, high sensitivity to magnetic field. I wanted this symmetry. It's easy to break this symmetry. Actually doing this photo association is a non-trivial step. And then, typical atoms you can start thinking about. Maybe you'll get F equals 3. Patterns are a little bit ambiguous. The flip side of that is maybe these Fs are places where there's interesting things happening. Okay. Finally, I just want to point out there's been a couple other proposals and even some experiments looking at dimer models in cold atoms. The most famous, of course, is Marcus's experiments with the tilted lattices, which you can interpret as 1D dimer models, right? That the things like can live on bonds. And Subir Sachdev talked both about these and about more generalizations in two-dimensional settings. The nice things about all of these ones is the energy scales are on the hopping level rather than on the superexchanged level. So there's some fundamentally better aspects of this stuff, right, on those grounds. Peter Zoller also had some nice ideas about using Rydberg atoms, and you can sort of understand that the geometric constraints come about from Rydberg blockade. Okay, with that, I'm gonna conclude. If you have any questions, please ask.
Someone in that class that we gave that problem to said, I'd like to work out this orthogonality for the entire many-body state. Then wouldn't they get a different answer?
So for the entire many-body states, actually, it's a nice exercise that if you take the overlap between any set of configuration like this, what?
Why not take the overlap not between those configurations, but between like a 100 by 100 lattice configuration?
Yeah, so suppose I wrote a 100 by 100 lattice configuration, I put a set of bonds on one, and I put a set of bonds on the other, right? So it turns out there's a geometric way to answer that you get, is that you lay the two patterns on top of each other, right? And you can imagine that when you lay two sets of bond patterns on top of each other, you're going to get a bunch of loops. You can express the overlap, I think it's at 2f plus 1 to the number of atoms divided by the square root of 2f plus 1 to the number of loops. Something like that. I'd have to write it down, but you can relate it to it's actually related to the number of loops in the system that when you do this overlap. So if you have a lot of bonds being different, then indeed you get a very small overlap. Right.
So with this photo association tuning, have you looked at what the off-resonance scattering rate is?
Yeah, I mean, so right. I mean, it's there's. Right, so essentially the question is how is omega related to your laser intensity, right? So what's the matrix element, and how big is your lifetime, right? Those are the two questions, and then you need to right. So how far can you tune? That's a question of your intensity, right? So in principle, right, based on gamma, you detune a certain distance, and then you ask, do I have enough laser intensity? Right? And our estimates were these whatever, however many watts per centimeter squared, and the.
Well, I guess you can only detune so far before you run into another line as well. Have you looked at this for any real atoms? I guess.
Yeah, so that's no. No. That's a mess, and there's so many lines, and this requirement that we're looking at in S equals 0, 1. Yeah.
Yeah, so I had a question. You mentioned this Winfield phase diagram.
Yeah.
So I didn't get it. Maybe you mentioned it. Are there any other calculations beyond Winfield?
So there is this exact ionization calculation. There's the mean field calculation. If you look at just the Roxor-Kivelson model, there are a lot of calculations on that. There's probably a dozen different approaches people use. A typical one is you map it onto a height model, and then there's a Monte Carlo algorithm that you can use on that. We've thought a little bit about some Monte Carlo algorithms that'll work on this model, but we haven't implemented any.
So how big is the exact diagonalization calculation?
So it was exactly the thing you were seeing. So it was 4 by 4.
It's a 4 by 4.
4 by 4. So not state of the art, but it, these things scale so badly, and really because we're looking at ordered phases that have certain symmetries. We want to keep to a square thing. And so 5 by 5, well, we have to go to 6 by 6 actually, right? And that's more work than it's worth, at least for us.
I was thinking, you were mentioning at the end Rydberg. Rydberg might be a way actually to induce your interaction shift. Because there at least the lifetime is longer, and the induced flashback resonance there actually has been demonstrated by Harry Washburn and I think some losses are bad, but
yeah.
It's better than on the lower states.
Yeah, thank you.
Okay, so I think we should move to a coffee break and come back at 10:20.
good. Let's do that. Okay, but it will be about Fermi-Hubbard system, but it will be about driven Fermi-Hubbard system, driven lattices, and some things are new, and so they are not will not be so smooth. So that's how it is. Okay, but let me maybe start with one thought. So there are some steps. And maybe some of you have had conversations with people from condensed matter, and usually condensed matter people say, in cold gases you never make a discovery. What discovery have you made? There's always this complaint. I don't know, maybe it's only the complaint to me. But I think there's actually a reason why there is not such thing that traditionally in condensed matter you would consider as a discovery. And I think the reason is that in quantum gases we always have this step-by-step approach. We move one step forward, then we understand it, and then the next step kind of is never a super huge step. It's just the next step, and then we see what kind of we had anticipated. I mean, a good example is of course the BEC-BCS crossover. I mean, it's not that you and the others that they just were in the looked at all the periodic table and trying out gases, cooling them and changing magnetic field, and whoops, at 800 something Gauss, lithium becomes superfluid. So it is a step-by-step approach, and then you do not have this these type of discoveries. So I think there's nothing wrong about the approach we have. Okay, so I had these steps, and then I thought, okay, I'll put my talk into these steps, so one could wonder what can one do with some non-trivial topology and interactions. I mean, how would you proceed in a cold atoms experiment? So first thing is you would try to start with some trivial topology, at least to have some topology in the system. So for example, a graphene. And then next step would be, okay, some non-trivial topology. So maybe by shaking, and then you might get some non-trivial topology in the system, but without interactions. Okay, and then you think, okay, maybe one should put interactions, but by putting interactions, you already, of course, run into problems. So how does actually a shaken system, how does that work under interactions if you have Hubbard use and so forth? And that will be part of the talk. And then one could wonder, okay, can one get a step further that these interactions induce phases when hopping? Okay, so that's specific on if there is a neighboring atom that you can get a certain phase. And there again, you would start to do that on double wells, on a simple system to understand how it works. Okay, so let me briefly remind you of the lattice geometry that we have. We overlay two lattices, and then we get, for example, this honeycomb type of lattice, which has A and B sublattices, and we can, and we will do later on, one can tune those, and one can, of course, also control how much tunneling you want to have. You can suppress it, and you have an array of double wells, or you can couple them, and then you have a Hubbard system. And then this lattice can also be shaken, so it can in two dimensions most of the time. We will, however, in this talk only shake along one direction. I mean, if you do this shaking, there we could show some time ago that you can use this shaking, that in this non-interacting system, the effective Hamiltonian has some complex next nearest neighbor tunneling, and this allows one to create a model system which has for example, a topologically Chern insulating phase. Okay, but
what about interactions? I mean, combining, for example, the Haldane model with interaction, there was some nice theoretical work by Pävi and also Matthias Steuer and others, and they showed that, okay, if you have interactions in this Hubbard-Haldane model, you will actually see additional new phases, and interesting physics will come up. Okay, but from experimentalists, there are, okay, they stop dreaming often, and then they wonder, okay, what is really on the tablet, and that's a question heating. Usually, when people shake lattices, they observe that it heats and it's a mess. But in the first part of the talk, I would like to emphasize that that's not true. That's not necessarily true. Depending on how you do it, this is actually for quite a long period of time, you can actually work with these driven Hamiltonians. And then you also wonder, how can you do magnetism in these driven Hamiltonians? And then there one can also show, yes, indeed, by driving, you can even make it stronger, the magnetism, or the exchange interaction, you can increase. And then in the last part there, I will report on this very recent work where we used interactions to induce a gauge field. Okay, so let's start with the double well, with a simple double well, okay? In the double well, you can tunnel and you have the on-site interaction U. Now let's assume we shake the double well, and then in this shaken frame, it's as if you do a time-dependent modulation of the site offset. So that is kind of the simplest bit of the model. We will later see a lot of situations where we connect, where we have a full Hubbard model, but for simplicity, let's look at the processes which we have here. The one thing that happens, the first thing that happens is that that your tunneling will be renormalized. And of course, there was Ennio Arimondo's work many years ago who did started with the shaking on the lattice and also look at the Mott insulator phase transition. At that time, I thought, oh, this must heat, and I didn't want to know. Okay, so this is one process, and then so you renormalize the tunnel coupling, but of course you may also have another atom on the other side with an offset, or if both are on one side, it makes an energy U. And you can also drive, I mean, so U is another frequency in your system, and you may wonder what's happening when you drive with the frequency U. Why not? But I mean, there's something is happening, so there needs to be some resonance. And this effectively will lead to some kind of density-induced hopping. So you can, if you have another site, you get this hopping process, which you drive, and you have a resonance where you can be either resonance either to the red or to the blue. And if you, for that system, if you then calculate your exchange interaction, so kind of the energy difference between singlet and triplet state, and then you can see that using the drive, a resonant drive, that you can modify your exchange interaction. And on a double well, if you measure it directly on the double well, you can see that actually the exchange interaction, if you drive a ready tuned, you can increase your exchange interaction. And so this is double well, but we did, and I'll show you later, we did experiments in a coupled system and could see that indeed our magnetic correlations increased when driving. Okay, so now let's come to the shaking of the whole Hubbard model. So you have your whole coupled Hubbard model, still, I mean, the same underlying structure, but you have strong coupling on these bonds as well. And there again, there are two regimes. One regime is kind of off-resonantly driven, which is meaning you're not driving with a frequency close to U. And then you just change the hopping. You renormalize the hopping with this Bessel function. And if you resonantly drive, then you change also the hopping term, but you also have a density-induced hopping, and you effectively change your U. So you effectively change your U by exactly this frequency. And now one can wonder, okay, what is actually happening in such a Hamiltonian? How can I test whether this Hamiltonian makes sense to play with? Does that describe the physics that I see? Is that experimentally a useful Hamiltonian? And the first thing is that we just look at losses and this type of approach. So this is the first thing, but then you see these two colors, blue and red, and there the idea will be that we compare the same driven and undriven Hamiltonians and measure, say, the double occupancy as a function of time and do a quantum simulation of the driven Hamiltonian with the equivalent static one. Okay, but first I want to take your worry about driven systems. And the reason why it seems that we were a bit luckier with driving the system is actually originates in our hexagonal lattice structure. So we compared cubic with dimerized and then hexagonal lattice structure. And well, if one has, and then, okay, the results are here's just the relative atom number relative to the beginning, and then we drive with a certain frequency, and we drive for a modulation time of 1 second. So quite a while. So it's a good time. And here we see the hexagonal lattice. There we see that for a large frequency range, we see not too much loss. Yes.
Is this the off-resonant driving here?
This is now well over the whole frequency range. It may include U's. It may include which U that is. This is 700 hertz here, and the U will be on the next slide. Yeah. So this is 700 hertz. So it's more reflects the non-interacting. But it seems that the main point is that the lattice structure of this hexagonal lattice has along this direction, and the band structure has the excited bands are flat, very flat. And that's because of this missing bond. And this allows you to drive along this direction over a large frequency range. You don't have states there. And as compared, for example, simple cubic that has quite a dispersion, and then you hit resonances, and that's why you get these losses fairly early. So this blue curve is a cubic, and the dimerized is somewhere in between with some sharper resonances. So it seems, at least that's our conclusion, that depending on the band structure, you just have to be careful, and and then you may find such windows.
Can I ask one more question?
Yes, sure.
Is that a real feature? It looks like around between 4 and 5 kilohertz, something peaks in the blue and dips in the green, or is that just a coincidence?
I'm pretty sure that's a real feature. Yeah.
The there's nothing on this planet 4 or 5 kilohertz.
Yeah, but it's multiphoton. You hit multiphoton. It's avoiding multiphoton resonances, and there is probably a multiphoton resonance, and then yeah. And then the other question that you had now, as a function of u, so the whole, so here it's u. The horizontal axis is u, of course using Feshbach resonance, and the static lattice are the red curves. So that's what you have in relative atom number after 1 second in the static lattice, the red curve. And for a shaking of 2.5 kilohertz, that's the blue points. So it's not too bad. Here it's getting a bit worse at higher frequencies. And the black curves are 4.25. Again, there are regions where you can work fairly well. Okay, it's 1 second, so it's really it's a long time. It's a long time. Okay, so now one may ask the question, well, what are actually the timescales? Can one measure somehow the timescales? I mean, you have some observable, and that will be double occupancies, and you switch your drive on, and then you may change some parameter, the tunneling or the effective U, and then you want to see what is happening with this observable, and that might change over a certain time. There might be local changes, kind of, because this observable feels, okay, now I can tunnel to the neighbor. And then there are longer processes where kind of the whole trap plays a role, and which are more take more time. And then at some point, heating will kick in. That is unavoidable. But the question is somehow how long are these timescales, and can one do something there? And so here the first set of measurements is a comparison between undriven and driven systems. So blue, undriven, driven is the right, and it's off-resonantly driven. So meaning off-resonantly compared to U. And we do a ramp in the tunnel matrix element, and we measure the double occupancy, and we ramp the tunneling down, and that results in a reduce. It's getting more Mott insulating in a reduce of double occupancy, and here is the time scale, and then at some point the system heats up or rethermalizes on a global scale, and it goes up. And here we can see over, I mean, basically the whole 100 driving cycles, that it's fairly equivalent, these two Hamiltonians, what we see. And this yellow curve is if we start with the final Hamiltonian initially, so kind of it approaches the final the value that you would expect for that Hamiltonian. And then we could also look at longer timescales, and there we kind of went to a region where we had more tunnel coupling, larger tunnel coupling, but again doing a similar quench. Again, off-resonantly driven, and then we can see this going up, and finally the heating kicking in on longer timescales. And here we can also see that at some point we lose atoms in the driven system. But again, over a good time, we have the effective Hamiltonian describes the system well. And then we also looked at resonantly driven Hamiltonians. And there, in the experiment, we start in the Mott insulating, and then we change U to some final value in a ramp. We first make a jump, and then, and also, well, that in the undriven system it's a spin flip, and then we go in a ramp to, say, a non-interacting, repulsive, or attractively interacting system. And then we watch what is the evolution, the time evolution in the Hamiltonian of the double occupancy. And we can see that for the non-interacting, repulsive interacting, and attractive interaction apart from the red curve, we get again very good agreement between the effective Hamiltonian and so the driven Hamiltonian and the equivalent static Hamiltonian. And here this red curve that has, well, the green curve agrees well, the red curve has a different protocol to compare with, so that's a subtlety. Okay, so briefly I want to show you, without discussing too much in detail, the magnetic correlations in driven lattices. Off-resonantly, there one can show, also show that you get in the effective Hamiltonian, you get for short time scales, I think that was 20, 30, 40 milliseconds, you get the same level of magnetic correlations as in the equivalent static one. If you drive resonantly, you can even enhance the magnetic correlations because you can enhance the exchange energy. Okay, so that was the part where I wanted to kind of convey the message that these driven Hamiltonians, if one is a bit careful, one should think about driving, and the driving enhances kind of the playing field that you have. And now the question is, well, what could one do with the driving? And a system which one would like to have is something, I mean, we do have these lattices and the particle can hop, and you might have some tunneling, and it might have some phase. But it would be nice to have a situation where, well, if the particle hops on this other bond and hops onto a situation where there is a particle on the other side, that then you actually acquire a different phase. So if you could control the phase that the particles acquire depending on, well, for the red particles, depending on what green particles you have to get some dynamical type of gauge fields. And we looked at that situation on an array of double wells, on bonds. And using now two driving frequencies. So we not only drive with one, but we drive with two frequencies, and then we get full control of this phase relative to the phase that is for the single particle. And we can measure that. Okay, so the idea is, well, we start off with a small sublattice offset, and then we drive the transition. So we prepare singlets, and then we drive with two frequencies to the doublon. So we couple the singlet to the doublon via two processes, via a process where 2 omega is u, or 2 times 1 omega is the energy difference. So we have kind of, it's like driving with two modes, and these two modes, how we drive, their phase we can control. So it's, well, that is basically kind of the driving frequency in time that we have, and depending on a relative phase, the pattern changes, and we also have, of course, control of the common phase. And if you, well, the question is always how could one relate that to something else? And since it's all new, I'm not so sure how good examples I bring, but one option is if you think of the situation that you have a ground state atom, an excited state atom, and now you drive it with a laser field, and you may drive it with two modes with a second laser field. And now, of course, you can drive it, well, when you interfere those two modes, you can determine by the phase, you can determine how it's driven, and you even can make it go to zero, because if the one laser field goes up and the other goes down, then your excitation vanishes. And this control you also have in our system singlet to double occupancy. Okay. And now, okay, and this gives a tunneling matrix element which has this form, where this alpha and beta, they are functions of our case, well, our drive, our driving amplitudes. But one can write it in this way, and there you can already see that if beta is larger than alpha, and you create a negative sign here, then you can have a sign change in your tunneling. And you can, of course, all create all different type of phases, and you can wrap around and have a sign change. We will see that this has the structure of a Dirac point, this matrix element. And, well, I had shown you this one, that was a 2 drive. And now we have to compare it to the situation where there is no atom on the other side. So we need to compare it to, relative to something. And since it's difficult just to blow away the atoms and so on, that is tricky. But what one can do, we can use a radio frequency to another internal state. So it was early on, it was red, I think here, that one, and we can make it green. And there we can make a Hamiltonian where the U is exactly the delta, and where this energy is equal. And that is our Hamiltonian with which we can compare our engineered Hamiltonian. And here this matrix element has a slightly different, it has a different character, because here's a sign, so you cannot fully wrap around. But the reason is because you don't have this, it's not sensitive to this second drive, so this one phase is missing. But this is our Hamiltonian to compare with. Okay, and then, okay, we do two types of measurement. One measurement is to measure the absolute value of this T effective. And that is a Landau-Zehner type of sweep. And if there is always a gap, so if when we hit the resonance, when we hit the point of interest, if there is a gap, then our system will simply go from the singlet initial state to the double occupancy, which we can measure. So we can measure singlets and we can measure double occupancies. And of course, if the gap goes to zero, if we are in a situation that those two terms cancel each other, then we will have reduced double occupancies, or ideally no double occupancies. And we can make such a measurement. So let's first make this measurement of just the absolute value of this matrix element, and that's shown here. And this is in the space of the driving. So this K1 and K2 are the two parameters of this driving, one of the one frequency, one of the other frequency. And we can see that here, well, the theory line is here. That's where you should have vanishing vanishing double occupancy on this green line. And we see we have a minimum. We have not completely vanishing double occupancy, and particularly not up here. But that's not so surprising because we want to bring down this matrix element to 0. And out here, alpha and beta are bigger, and then it's more difficult to get, to get your angle exactly right. So any fluctuation will give you a finite value. So we are not too unhappy with those measurements, but of course the question is also what is the phase? It would be nice to see that there is a change in the phase when it goes to through 0. So one would like to know this, what's happening as a function of phase. Okay, and to measure, perfect, yeah. To measure the phase, we have the following measurement protocol. So this brown Hamiltonian, that is the Hamiltonian with the drive. That's when we have the kind of the interacting and driven Hamiltonian. And what we do is we start with a singlet, and then we adiabatically prepare the state on the equator. So we go, well, adiabatically up with this Hamiltonian. And then we switch to the other Hamiltonian, which is along the x-axis. And then we let the system evolve and measure the double occupancy. So then this would go, say, if it started here, it would go up and down again. So that's how we make the measurements. And this is here you see, this is this adiabatic preparation. Then we have as many singlets as doublets, as double occupancies. And then we see these Rabi oscillations in the effective Hamiltonian. And now we do this measurement. We determine what a pi half pulse is. And then we can measure when we go on to this point, and then we measure the relative phase between these two Hamiltonians. We measure them as a function, so this relative phase changes with the common phase of both. Okay, so we change this phase, we continuously move this, and then we can extract this relative phase between the two Hamiltonians. And that is here we this absolute phase is changed, and then we see this kind of Ramsey fringes, and from those we can determine the relative phase. And now we can plot. So we have this. Well, I've shown you earlier this gap closing transition, and now we can measure along this line what is the relative phase doing, and that is, well, the green line. It maybe should have been the blue line. Anyway, and there we can see that we have indeed a jump in the phase by approximately 180 degrees. And then we can also now go into, that's the last slide, we go into we take a certain K1 and K2, our driving parameters, and change the relative phase, and then we can measure and we see how the double occupancy goes to 0 here at the Dirac point. And here we can also measure, so there are two relative phases, there are many relative phases. So that's the relative phase of the driving, and then we have the phase between the two Hamiltonians, and there we can see that this Hamiltonian has this vortex type of structure, and here are some pictures of those. And well, with this I come to the concluding slide on that. I should also mention there has been a few days ago by Fabian and co-workers a proposal with a single drive which doesn't have this Dirac point structure, but there are, I had not had yet the time yet to read through it, but I think there are a lot of similarities. We'll see that. And here, well, this is a very busy picture, so you have these Dirac points on the doublets, but if it's single, then you have an open gap, so one will see what one can do with that. But I would very much like to thank the people, and I should point out that Frederik Görg, he and also Kilian Sandholzer, they were, yes, they really came up with that scheme and measured, and yeah, so I would like to thank them and the whole team, of course, very much. So thank you very much for your attention.
Yeah, very nice so much. It's really amazing to have this new tool to have a gauge field that depends on population of atoms. So if you could dream a bit, what would all become possible? It seems to me, I mean, things like dynamic gauge fields, which would then allow you to make models that link to very different fields of physics. But what?
Well, yes, of course, that's the hope. But we had not so much time so far to dream. Yes. It was actually, it worked surprisingly well. That was a nice thing. I mean, yes, it just worked. I mean, sometimes, you know, you work hard and doesn't work, but that was okay. We tried this, and I think I was on holiday or on a conference. and then I got this data saying, no, we see these Ramsey fringes, we work this and this works. I hope that, of course, you can start coupling. I think that experimentally should not be too difficult. And then maybe you can prepare with the spins in, well, the way how you prepare the other states. You get a certain, well, you can prepare the way how you can get phases depending on the density. And then that might have influence on the whole scheme. You can think about, do you have some sort of edge states in these systems? But I cannot give you conclusive answers because we have to think about that. And then, of course, one has these ideas and then one has to check where are the problems, as usual.
So I haven't really understood what Hamiltonian that you have produced. Do you produce the usual hardware Hamiltonian, but now with a hopping that is number dependent?
Yeah. It's. I mean, the Hamiltonian at the end reduces to well, it's on a double well with an offset, and then you couple the singlet state to the double occupied on one of the sides. So there's like some offset, and that makes sure that you couple to only this and not to the other one. In principle, you could also, but the most simple form is you couple only to that one, and you couple to it via two driving frequencies. Kind of you have this density-assisted hopping, but with two frequencies. And with two frequencies, that allows you to get the control of the phase.
Right, but the Hamiltonian is just the tunneling phase depends on population.
Yes. Yes.
Okay.
Yeah. Yeah.
So for the case of the one frequency drive and not in the double well, what were you
Yes.
many bodies uniform system? Has anyone? Do we have any idea what the phase diagram is?
I think that isn't that for the one frequency drive more or less in your paper. I thought that's how I understood from our brief conversation that you looked at the ladder with a one frequency drive and then at, well, what the ladder phase is in a bosonic case, though, I think. That's.
I mean, there are so many tuning knobs, right? So, because you can tune the phase, and that very sensitively depends on the phase. And
for
You can also tune, but you don't get the wraparound. You for one frequency you get kind of, that was. But this type of, I think that's the type you have also. Yeah. But okay, thanks.
While maybe it's preparing, if there are some other questions, we can take another one. No? Thanks to the speaker.
The microphone, huh? I wanted to kind of like keep commenting. So.
You have that two screen, maybe? Maybe you can put on one screen.
What happens now? Let's do it. Okay. Put this meanwhile.
So we have to change HDMI from.
I had also HDMI.
You also had
I was on HDMI.
Usually it automatically detects it.
I don't know. If I try once more.
Yeah, try it again.
Maybe you have to press.
No, you have it on the screen.
No? Okay.
Now you open and it's showing another screen. Yes. This is another screen.
Oh.
Can you duplicate the screen? So you're going
Actually,
to
just start it. Just start the presentation.
Yeah, it probably goes when I put the slideshow on. Yeah. Okay. Thank you. Okay. Thank you. Yeah. Good morning, everybody, and thank you for the organizers for inviting me here. It has been a really wonderful conference. So, this is the contents of my talk. I will first advertise some other papers that I won't talk about, just in case somebody wants to discuss those with me in the coffee break or something. I don't know. It's strange to be so far. Yeah. And this is, yeah, maybe better be here. Yeah, then I will give some kind of a one-slide micro talks about our DMFT studies, 2 of them. And then finally I focus on the main topic, geometric origin of flat band superconductivity. And there I tell some stuff that I have told before, but I will tell something new that is not even in the archive yet. So, and here is the main message that's related to the new part. So if you don't remember anything else from this talk, this is what I would like you to remember, that we have considered the two-body problem of two attractively interacting particles in the flat band. And that already tells really surprisingly much about superconductivity in a flat band. Maybe it can even, give the essentials when you can have it. Okay, but these are these other works. So Tillman actually advertised this first one already, thank you. And then we have some other stuff. We have done a lot of work on FFLO, so if anybody is interested, including a review. And we have finally shown that the superfluid density is non-zero there. And then I have also experimental activity in the group. We have observed a new type of BC. But then let's go to this small talks about our DMFT study. So here we considered the very classic problem of doped, repulsively attractive Hubbard model. And you all know that there is a suggestion of D-wave superfluid at some parameter regimes. But there are also suggestions that this is competing with a stripe phase, so where the magnetization is modulated in space.
And people have looked at both of those things with advanced methods, but we now looked both of them at the same time with cluster DMFT so that we can go beyond mean field. And we found that they can coexist. So this is as a function of doping the average magnetization. And this is the D-wave superconductivity parameter. And this is the wavelength of the stripes. And we can find regimes where they really coexist. And also in a kind of funny, unexpected way, that you would have the maximum of D-wave superfluidity and magnetization at the same position. Okay, so that's one. And then another work, yeah?
What lambda was it?
Lambda was, so these stripes are like a staggered magnetization. So that's the wavelength of that magnetization. So we plug it in as a parameter. And then we see what gives the minimum energy. Okay, then another DMFT work. Here we looked at Lieb lattice, which has a flat band. So I have this, I'm really fascinated about this flat band. So there, for instance, the normal state can be quite unusual. So we found that near the flat band, one can find a non-magnetic and non-Fermi liquid metal normal state, plus some other more usual phases. Okay, so then I go to the main topic, and we have had a bunch of papers on this, and this is the new stuff. It's not yet published, but it will be in the archive very soon, depending on how much I manage to work on the flight back. So, basics. Now, periodic structures have, they fulfill the Block theorem. So you have eigenfunctions like this. This is the Block function. This is the periodic part of the Block function. And this is a very important quantity for my talk and also in general. So in this Percy band, you have some non-zero bandwidth. Flat band means that, well, it's flat. Basically, the group velocity is 0. And the flat band, I don't mean it needs to be exactly flat, just that if you're looking at interaction phenomena, the interaction is quite much bigger than the bandwidth. Then you will start to see maybe flat band effects. Okay, a lot of interesting stuff happens in flat bands because obviously interactions dominate. Also, you may think that quantum fluctuations and disorder and those also would be stronger than usually. But I have been interested in pairing, and already the BCS theory gives a dramatic difference between dispersive band. This is the formula that you learn at school, and now if you do a BCS prediction for TC in a flat band, it actually becomes linearly dependent on the interaction times the volume of the flat band. So it's hugely different. And this can lead, in principle, to very high critical temperatures. So maybe a flat band would be the route, eventually to room temperature superconductors, which I think we are all after in the end. This? V flat band. This is the volume of the flat band. So it's just integrate all called K momenta that you have there. Okay, but so this prediction has been there for a while, but we wanted to ask that is it actually a superfluid? Because your, let's say, naive picture of a flat band is that nothing moves because group velocity is 0. And actually, if you do the simplest theory of superfluid weight or superfluid density, it's 0 because of this thing. So we started to look at this question. And it turns out to be that these Block functions, these ones, are extremely important in this question. And you know that they are also related to topological quantities. So Berry curvature is basically given by derivatives of the Block function, and of course then the Z number when you integrate over Brillouin zone. So these things will come up. And here is again the main message of our investigations. So we can show that indeed there is superfluidity in a flat band, and that actually in general is connected to a quantity called quantum metric. And what's that? Well, this is what the name says. So these people wanted to make a definition for quantum metric in a sense that if you make an infinitesimal change in a parameter, how does your wave function change? So how far is the state when you make this small change? And then you can show that it looks like this. And this is actually not a gauge invariant, so they did some further steps to make it gauge invariant. And from that, they define this kind of tensor called quantum geometric tensor. And its real part is now the quantum metric, which is really just describing what is the infinitesimal distance in this submanifold of your Hilbert space. And then the imaginary part is Berry curvature. So there was a connection to these things in this object. And this quantum metric in some other communities is called the Fubini study metric, and it's also related to Fisher information. It's not exactly the same, but yeah, related. And this quantum metric is only emerging in physics, I would say. So there are these two siblings, the Berry curvature and the quantum metric parts of the same tensor. And you know, Berry curvature is already extremely famous and has been observed many contexts and so on. But the quantum metric, well, there is some theory work now in recent years, actually even in this decade, all of them. And what comes to experiments, it is sort of inside in these experiments, but has not been explicitly discussed. And now there is a first cold gas experiment where they have seen the Brillouin zone integrated quantum metric in Hamburg. So I think it's an interesting quantity to look at, and maybe we will learn a lot what is the significance of this quantity in physics. Then about flat bands. So why are they interesting? Well, I already said that all interaction effects and so on will be large, but also because you guys can create them. So one can have flat bands in lattices where you have a more complicated units and like Lieb lattice. This is from Professor Takahashi's papers. So for instance, in Lieb lattice, you can think that you can have a wave function where you have a plus sign here and minus sign here, and then they interfere and you will have nothing on the A side. So this is the basic mechanism of creating flat bands. Then you kind of block the movement by interference effects. Another way is to take some systems where you have fluxes, because then you can have flat band basically by creating Landau levels. And then, of course, there is this recent discovery, I think in the sense of Tillman-Esslinger, of this magic angle bilayer graphene superconductivity, which we will hear more about tonight. And that's really interesting because the superconductivity appears when the Fermi level, when the Fermi level is at a flat band. So by changing some parameters, basically the angle, they can have different kind of band structures, and the superconductivity coincides with the flat band. So this, I think, is really exciting. And then I want to take this step-by-step approach to try to understand superconductivity in a flat band, starting from very, very basic things, like today I will show even the two-body calculations. Okay, but let's first see what we have seen from many-body calculations. So, by the way, so in order to answer whether there is superfluidity in a flat band, we calculate the superfluid weight. It's defined like this. It's basically the same as superfluid density, but now defined in a lattice context. So you can introduce a Cooper pair momentum in your Hamiltonian and calculate, for instance, the free energy chains. And from there you get the superfluid density, and it should be positive and non-zero so that you can have supercurrent. So in other words, it's like seeing the stability of your system to a phase twist. There are also other ways of determining it, but this is the essential quantity. And you really need to have it non-zero to have the defining properties of superfluidity, because you could have large pairing, but still no superfluidity. This trivial example is an optical lattice with huge barriers between the sides. So you have a flat band, but that's a trivial one. You have only pairing, no superfluidity. Okay, so we go for this one. And we calculated first using multiband PCS theory. So all these systems where we can have interesting results, they must have multiple bands and attractive interactions. And we define order parameter. And then we calculate the superfluid density. And this is the essentials of the result. So the superfluid density will have a part that is the same as obtained earlier. It's the like derivatives of the dispersion, and this is of course zero in a flat band. But there is another contribution that we call geometric, and this one can be non-zero in a flat band. So that's the essential one. And this is present only in multiband case. So in the usual single band Haber-Mohr, for instance, is zero. And then when we look at closer this geometric part, we can get nice analytical result if we assume that the flat band is separated by other bands sufficiently, and so that the interaction is so small that you don't put particles on the other bands. And of course we have to have the flat band, so bandwidth smaller than the interaction. And then furthermore, we assume uniform pairing, so that in all orbitals we have same pairing. And in this case, the results become very clear. So we recover this linear dependence on the coupling that was also obtained for the pairing gap. So it's the same comes for the superfluid density. And then this is filling, so there is some filling dependence, numbers of orbitals. And then this one now contains the quantum metric that I talked about, integrated over the Brillouin zone. So this geometric quantity determines whether you can have superfluidity in a flat band. So as a reminder, this was this quantum metric, and you remember it had a connection to Berry curvature because it's part of the tensor whose imaginary part is Berry curvature, and then we can use that one and the positive semi-definiteness of this tensor to derive a lower bound for superfluid density. And this is that whenever you have either non-zero Chen number, or even if this is zero, if you just have non-zero Berry curvature somewhere in the band, then you are guaranteed to have superfluidity in the system. Okay, so that was based on mean field PCS theory in the multiband context. And of course we want to, everybody asks, well, this is the mean field, how is the validity, especially in flat bands where the fluctuations can be large. So we have done a lot of further work. We showed the same results by perturbation theory, and then we compared the exact diagonalization, DMFT and DMRT in certain model systems. So we have benchmarked this, at least in some cases, to more exact methods, and the result is the same. And we also did some semi-classical thing, so we pretty much believe it. And now I would like to discuss a bit what is the physics behind all this. So the essential things are overlap of the one-year functions and that you must have a multiband process present. So in this picture, I have now a single flat band, meaning that the transport is 0. So that would be like a single band system. You don't have overlap of the one-year functions. And nothing moves. Okay, then if you have a multiband system with a flat band, you can have large overlap of the one-year functions, but particles don't move simply because of these interference effects of wave functions. Now when you add interactions, if you had this kind of trivial flat band, like a very deep optical lattice, you still don't see any transport. But now in the multiband system, because you have large overlap of the one-year functions, you get some kind of induced pair hopping, induced by interactions. And mathematically speaking, now it's easier maybe to understand the connection to the Chern number and so on, because it has been shown that if you have non-zero Chern number, then your one-year functions cannot be localized. So this somehow guarantees this overlap of one-year functions. These topological properties guarantee that, and that's needed. And then in this work where we derived the effective Hamiltonian, we could end up with this kind of spin Hamiltonian, where these are pair creations at the different sites. And you can see that the pairs can hop if this is non-zero, this tunneling matrix element, and that turns out to be exactly this overlap between one-year functions. And this interaction-induced pair hopping has been predicted for bosons by Ehud and Sebastian Huber. And then I would also like to remind a paper by Leggett, where he looked at supersolids, and he also showed that somehow for this solid to be also super, you have to have always a density, so you cannot put the density to 0. Otherwise, you cannot establish a phase. So it's a bit similar to this. And then what about experiments? So what happens at high temperatures or finite temperatures? What were the things that you should look at? Well, basically, it's this linear scaling in U that is the essential thing. And most dramatic effects are for small values of U, like maybe like around 1 hopping or something. And here we have calculated the BKT temperature and BCS for the flat bands, go like this. So this is the BKT, and this is for dispersive band. And if this zoomed up shows that especially for small interactions, these flat bands are dramatically better. And then for larger interactions, actually dispersive bands win. So this, of course, then makes one ask what happens above these critical temperatures. Do we know something about the normal state? And we have one study about that, where we looked at what happens in this type of Kreutz lattice when we put a flux in it. And I don't say much about this because I want to show the new stuff. But basically we showed that the carriers of current are always pairs, also in high temperatures. So one could see this kind of pair movement and localization of single particles also in the normal state. Okay, so now I go to this unpublished stuff. So I have all this explanation of the thing, but I was never very fully happy about the understanding that we have about this phenomenon. So I thought that, okay, let's look at the two-body problem in the same way as the Cooper problem was studied for superconductors by Cooper. And as a reminder, there you just look at two particles and add the Fermi C, which prevents scattering. And from that calculation, you actually get pretty much the the features, basic features of BCS type of pairing, not quantitatively but qualitatively. But you have to add the Fermi C. If you just solve the two-body problem in a dispersive band, it has nothing to do with superconductivity. You won't have a bound state. Okay, so now we have here the two-particle Schrödinger equation. So these now contain also the periodic potential, the lattice. And then there is interaction between the two particles. Lambda is the coefficient. And now in a flat band, we don't have a Fermi C. This is from the beginning very different from the Cooper problem. We don't have Fermi C. It's totally degenerate. And now what we claim is that we have to look at, of course, whether we have a bound state there, but not only whether there is bound state, but also whether this pair has a dispersion. Because single particles are hugely degenerate. And now if I create a pair, and if the pair is still degenerate, then it's very unlikely that I can create a superconductor because there is no preferred pair momentum where to go. But if the pair has a dispersion, then I can expect that there would be superfluidity, that the pair, I mean, there would be a minimum for momentum and you could sustain current, supercurrent. So let's look at this, and this is the solution. And here, this is the thing that is different now. I mean, this is a typical form for the scattering problem. But here at flat band, this is the flat band contribution, all energies are the same. So that's the different thing. And this can be solved, of course, exactly numerically, we have done it. But to obtain analytic solution, we take the isolated flat band approximation, so we neglect this one, and we use this separable potential approximation, which is often used and which is kind of okay for contact interaction. And this is the result. So this is now the binding energy. This should be negative to have a bound state. And okay, this is lambda. If you have attractive interaction, it's negative. Whenever this is non-zero. And the result is extremely simple. So this is the potential. And now x coordinate is like your orbital coordinate. We have a multi-band system. The potential can depend on the orbital. And this is simply the overlap between the wave functions of the two particles that are scattering. So since there is no kinetic energy in the flat band, it doesn't appear. It's just the overlap. And now we can see about this pair dispersion finite effective mass by looking at this thing. So obviously there has to be some non-trivial dependence on Q. Q is the pair momentum in order to have this dispersion. So we expand this for a small q, and the result looks like this. So this is the binding energy, and you see here is Q times Q, so this is the inverse effective mass. It's written here. Effective mass is now given by derivatives of this kind of projector which just contains the Bloch functions. So these Bloch function derivatives will tell you whether there is a dispersion for the pair. And this result, by the way, this is a gauge invariant and basis invariant. It's very general, even when there are approximations. And then if we further assume that this pairing potential would be independent of orbital, so this kind of uniform pairing, then we get the same result as from the BCS mean field theory. So that this effective mass is proportional to quantum metric. And so this superfluid density, it has, of course, you can define it's like the inverse of the effective mass. So we really get the same result as from multiband BCS theory. And this multiband BCS theory we had in some cases mapped to exact results. So this is quite interesting. It seems that the essentials of this flat band pairing can come out from the two-body problem, which I think is quite nice in various ways. First of all, if you have a very, very complicated system like bilayer graphene, so you might actually start to study the two-body problem in full detail to see what is going on, and also in the search of new superconductors. And then also, if it's mostly two-body physics, then maybe it's a robust effect, and one can indeed have these high temperatures. Of course, I mean, one has to then compare what comes up with quantum fluctuations. And maybe the other way around, like if we find a finite effective mass, then yeah, you can expect superfluidity. On the other hand, if we don't, this would also maybe be some very exotic many-body state then, because it's highly degenerate for the pairs. Then we looked at a couple of model systems that you could do in your lattices if you are bored with the square lattice. So for instance, this sawtooth ladder, this is the band structure. There is one flat band, and nicely it's the lowest one. And now the exact two-body problem gives you this kind of binding energies, and this analytical formula that I showed gives this one. So because there is this separable potential approximation, it actually gives only one bound state instead of all, and that's why it's a bit off. But the dispersion is, I mean, the effective mass you can still got correctly, so it's quite nice. So for this system, yeah, you have this pair dispersion. And then for the Lieb lattice as well, it works very well. This is the exact, and this is the analytical results. And here you can again see that there is pair dispersion. And I think I have 2 minutes or what? Yes. So I can propose an experiment for you, because maybe you want to explore other lattices than the square one, and this doesn't require extremely low temperatures. And things would be quite different from what you have seen so far. So there are many experiments where people look at, these are just two of many others, where people can monitor how things expand in a lattice. So I think this might be one of the easiest way of seeing these effects. So first, you would need to create a flat band lattice and put some kind of initial state there. And you could start with the dilute gas to just probe the two-body physics and later add more. And yeah, you have the initial state with some kind of initial trap or whatever, and then you see the expansion. And now this would be very different from many experiments that have been done, namely the non-interacting fermions or bosons, the two-body physics you can do with bosons, they should not propagate. So if you really have a flat band, they should be stuck. And then you put interactions, and then you should see propagation. Usually when you put on interactions, you have this t squared over u type of slower propagation. Now it should be much faster than in the non-interacting case, and it should be proportional to the interaction. So you tune that knob and it should go faster. And also it depends on these Bloch function derivatives. So if you change the type of lattice, it should be different. And yeah, for temperatures, the scales would be basically the scale of hopping. That's typically the band gap scale. U should be lower of the order of hopping, and then the temperature may be quarter of the hopping or something. Doesn't need to be like 1% or something. And that's my conclusion. So we have shown that the superfluidity in a flat band is possible. It's guaranteed by topological and geometrical quantities, and the two-body problem already seems to give much of the essentials of this phenomenon. And here are the people in particular, well, our ETH collaborators, Sebastian Huber on some of the parts, and then Sebastiano Peotta and Long Lian are the two very important postdocs in this work. Both are searching for positions if you are interested. Thank you.
showed an expression for the superfluid density as a function of filling,
Yeah.
where it vanished at the nu equals 1 and nu equals 0.
Yes.
So in quantum Monte Carlo simulations of the attractive Hubbard model on a linked lattice, you see a minimum of the pair structure factor at those fillings because of a competition with charge density wave formation. Is that why your d sub s is vanishing there also, or is it just low filling?
It's just more like low filling because this is PCS theory. It doesn't take into account this competition with the charge wave. Yeah, no.
Maybe I had two questions. One is, at the end of your talk, you said if you have a flat band and you have non-interacting particles, they would not expand because
Yeah.
Book velocity is 0. But if you have then interactions, because now I want to really understand it, the pairs have now dispersion, that's why they expand.
Yeah.
Should I now regard at the expansion in the interacting system as an expansion of pairs or of single atoms? And then if it is an expansion of pairs, an effective velocity is always you hop one lattice constant in a tunneling time. Is the tunneling time for the pairs now a super exchange time j square over u?
Yeah, so to answer first question, yes, it would be movement of the pairs and single particles. It's funny, at least in some systems that we have studied, single particles really would stay stuck also in a case of interaction. So if you have an imbalance system, only the pairs would propagate and the single extra particles would get stuck. And then, yeah, this is the whole thing. This velocity of the pairs or effective mass, it has now nothing to do with this t squared over u. It's not a super exchange process. So it's linearly proportional to u, linearly proportional to the coupling. And then it depends on some properties of the Bloch functions of the multiband system. So it would be very different velocity. So it's like an interaction-induced hopping. So it's not a super exchange process.
Is there a simple model for that? Or?
I think the simple way to understand, but the simple way to understand it is that you have the localized states take a basis of localized one-year orbitals in the flat band, right? And they're orthogonal one-year orbitals. Since they overlap spatially, there is interaction between them. So the interaction has kind of 4 particles. Once you apply the interaction within that space, basically it generates pair hopping, right? So you have no kinetic energy. You just have a basis of states that are not completely local. They're local over.
Yeah. So
And if you just apply the localized spaces, right? You are delocalized.
Yeah. The one-year functions are never localized. They are always overlapping with the neighboring sites. So you cannot, in a way, to think that your particle is in one site only because the one-year functions are delocalized.
My second question is, what really depends on the presence of multibands? Because you can have a single band which is a flat band. I don't know, your two-body problem was probably solved in the single flat band. But if, Curvature and those things come in, this is usually only present if you have a multiband and you eliminate, the higher bands adiabatically. So what part of you said in terms of pairing and pair propagation requires multiband, or what would also happen in a single band?
So everything requires multiband. So if I have just a trivial single band system like the single band Hubbard model, I would not see this at all. But there is a thing, when I say here that I neglect explicitly this other band's contribution, that means that I focus on the physics of the flat band, but the existence of having many bands is now encoded in the Bloch functions. So the Bloch functions are calculated for the whole system. And that I have to do exactly by including all bands.
It's also related, I think, to what I said before, that if you have only a single band and you have localized one-year orbitals, they would have to be localized on one side.
Yeah.
And then the interaction would not do anything.
Yeah.
Unless it's not local.
If it's not local interaction, you will make discussion anyway.
Good.
It's only a local interaction.
There is one question.
Yes. So I wonder when you say multi-band, it's like only one band is flat band, others are not. Is that correct? Or all the bands are flat band?
Well, this doesn't really. Yeah, question was, does it matter whether all the bands or one band are flat and so on? It doesn't really matter. I always focus on the physics that happens in one flat band, but then there are many other, and those can be either dispersive or flat.
So I'm not sure whether I understand this correctly. So it's like the effect of multibands is you kind of create overlap between one-year functions on different lattice size.
Yes.
And it is the interaction that can coupling this one-year states on different sides.
Yeah, yeah, that's correct. Yeah, so the multi-band nature is essential for creating this overlapping one-year function, and then with interactions, hopping can be induced.
Well, I just wanted to know, is there any, is it sensible to think about the symmetry of the paired wave function, like you do in DCS theory?
Which symmetry?
Symmetry.
Yeah.
So, like orbital symmetry, S wave, P wave, pairing. I mean, is it sensible to think of in those terms, or is it you have to think in a different way?
Well, I think, we have so far looked at S-wave pairing. In one paper, we extended a bit, so these concepts don't get killed if you go to other types of pairings. And of course, in the two-body problem, this was assumed attractive interaction and contact interaction, the simplest case. But there one could easily extend it to some kind of effective attractive interaction between nearest sites, and that would be like the D-wave pairing or something.
And I guess this condition of Cooper pairing still holds that you'll get pairing for arbitrarily small lambdas, right?
Yeah.
This place is notoriously inaccessible to people with disabilities, as you may have noticed. We're in a hill and everything is. So while we break off to go for lunch in the library, we're going to